visiting amarpathshala.com. As you can see, this is the part 3, which is the final part of the chapter Chemical Bonds and the Structures of Substances. If you follow the previous part of this lecture, you will gain a full understanding about the different kind of chemical bonds that we find in elements and compounds. In this last part of the lecture, we dig deep into metallic bonding and macromolecular substances. To begin with, metallic bonding. What is a metallic bond? A metallic bond is a kind of a chemical bond that is found in metals. Now, what are metals? That is a question that was answered in the chapter periodic tables and their situation in a periodic table. So, if we look deep into a metallic bond, we will see that there are metal atoms that are held together in a very compact and an orderly arrangement inside a metallic bond. Each metal atom gives away some electrons, forming a positive ion, and the free electrons that it gives up then moves into the free spaces between these positive ions. Now, these positive ions are large, they cannot move, but the free electrons can move. As a result, the term delocalized was coined to them. If you follow metallic bonding in your textbook or anywhere, you might come across this term delocalized. This means that these electrons that are usually found embedded or moving around these positive ions, they are not fixated into a particular location, so they are delocalized. Therefore, in a metallic bond, it is often said that the bond is a positive ion, bond is formed of positive ion, embedded in a sea of electrons. You might be confused, why sea of electrons? Well, each positive ion, depending on the kind of metal that we are dealing with, gives away from 1 to several electrons, and they all are moving about in between the free spaces of these positive ions. As you can see in the diagram, this is a very simplified demonstration of a metallic bond. In here, you can see that these are the positive metal ions. And in here, in between the free spaces of these positive metal ions, the free electrons are kind of moving about, loitering. And as a result, they are called or known as delocalized. And their movement, due to their volume, obviously, their numbers are higher than the positive ions that are generally found. So, due to their number and their ability to move around, they are also known as a sea of electron on which the positive ions are sort of embedded. Now, what is the advantage of having a sea of electrons? See, when we were discussing ionic and covalent bonding, we said that ionic molecules conduct electricity only when they are either molten or dissolved in water. But we see in everyday usage or in every day of our life, we use and see metals conducting electricity in solid as well as when they're molten. So having these sea of electrons allows them to have agents that can carry electricity. As we know that the movement of electrons is what conveys electricity. So movement of these sea of electrons is what carries electrical energy or electricity through the metal. As a result, metals conduct electricity when they are solid, also when they are molten. And in a metallic bond, because the electrons are moving about, and obviously there is a strong electrostatic force of attraction between a negative electron and a positive ion, what happens is that this allows the metals to have a very strong bonding, and thus metals end up having with very high melting and boiling temperatures. Something that we discussed over and over when we were learning about ionic and covalent bond. So, not only do the free moving electrons gives metal an easy access of electricity conduction, they allow the metals to have a strong bonding due to the force of attraction, They cause the metals to have high boiling and melting temperature, and also the positioning and the arrangement of these ions and electrons allows metals to be very good conductors of heat. Let me tell you how. See, these are compactly packed metal atoms, and metal atoms in a compact structure, if you have studied physics, you know what the word or the kind of heat transfer, conduction, means. What is conduction? Conduction is a mode of heat transfer in which heat energy is transferred from one molecule to another through the form of vibrational energy. And as metals are A, solid, B, very orderly and compactly arranged, therefore this allows heat energy to travel between their molecules very efficiently, very easily. So metallic bonding, the type and kind, allows metals to have a strong compact structure. It allows them to have a high melting and boiling temperature. It allows them to conduct electricity very easily, even when in solid as well as molten, and they are good conductors of heat energy as well. Now I will construct a table for you, allowing you to see the different instances or the different advantages of a metallic bond. So guys, as you can see, this table summarizes some of the key features of a metallic bond. In here we see if the structure is metallic, the particles that are found in the solid are atoms or positive ions, metal atoms or positive ions. And the bonding between them is a strong metallic bond due to the attraction between the positive metal ions and the negative delocalized electrons. The boiling point, denoted by Bp here, as a result of the strong bond, tends to be very high. And metals are insoluble in water. This is because they are not exactly bonded like ionic particles are, wherein ionic bond holds the two ions together. Metals are when the electrons are moving around freely, and that is sort of a compact structural molecule, as a result of which metals alone tend to be insoluble in water. An example of metals composed of metallic bonds are magnesium, iron, etc. Guys, in this part we discuss about macromolecules. What are macromolecules? The word macro means big. So macromolecules are big molecules. These are molecules that are held together by strong covalent bonds, as a result of which they are also known as giant covalent molecules. Now, diamond is a macromolecule. In diamond, one carbon atom is joined together with strong covalent bond by 4 other carbon atoms. In the word macromolecular bonding, or in a macromolecular bonding, the entire atoms that are involved in making one molecule are combined together in one big bond formation. It's one giant molecule forming one giant bond forming the entire molecule. So when we see an example of a macromolecular substance for us in this context is diamond. In diamond, what we see is that it has a very complicated structural arrangement. Each carbon atom is strongly bonded with 4 other carbon atoms, and therefore they form this chair-shaped, complicated ring-like structure. Examples of other macromolecular substances are silicon, silicon dioxide, silicon and silicon dioxide. All these 3 molecules that I just mentioned have similar arrangement and similar structures. In case of silicon, one silicon atom is joined together in its macromolecular bond. One silicon atom is joined together by 4 other silicon molecules. In case of silicon dioxide, one silicon atom is joined by 4 oxygen molecules. So in macromolecular substances, our examples are diamond, which is composed chiefly of carbon, silicon and silicon dioxide. All of them, silicon dioxide is also what we know as sand. So in carbon forming diamond, silicon and sand, we have molecules made up of a compact macromolecular structure. Giant molecules, each atoms combined or bonded together by strong covalent bonds. What is the purpose of these strong covalent bonds? What are the advantages? Well, one thing is that because of these strong covalent bonds, they are very, very hard. See, diamond, for example, it is known as the hardest substance in the earth. You can cut glass with diamond, and apart from having it on your ring, apart from having it on you as a ring or any kind of ornament, and apart from it being beautiful and rare, it is also very, very abrasive. It can cause damage. And one other thing that macromolecular substances, one other characteristic that macromolecular substances possess is that they have very high boiling temperatures. Silicon, for example, has a melting temperature of 1410 degrees Celsius, and it boils at an even bigger temperature of 2360 degrees Celsius. So you see, they are, if you view them, they are simple molecules. They don't have complicated structures. They just complicated formulas. They don't have complicated formulas, but when you see them in details, you see that the bonding between them is so intricate, and the intricacy is so strong that overall they come off as chemical compounds that are too hard to tone down. They end up forming these giant substances. But due to the inability of these bonds allowing electrons to move freely between them, unlike that in metallic bonding, they don't conduct electricity. Diamond doesn't conduct electricity. None of these do. So what is that we learn between these bonds is that in metallic bonds we have positive ions around which negative electrons are moving quite freely. Thus, these metal atoms are able to conduct electricity, and metal having a compact orderly structure allows it to conduct heat as well. A metal can conduct heat and electricity when solid and in molten state, obviously. And in case of macromolecular substances, we learned that these molecules are known as macro or big molecules. The atoms of these molecules are held together by strong covalent bonds, which is also why they are known as giant covalent molecules. And all the atoms make up this one big molecule, forming their structure. Examples of macromolecules are diamond, carbon atoms forming diamond, silicon and silicon dioxide for this context. And examples of other macromolecules are, for example, polymers, but we are not going to discuss it in this chapter. Following this diagram, I am going to present in front of you a table which details some of the key differences between an ionic bond, a covalent bond, and a macromolecule. So I hope you find that table useful. So guys, as you can see, this table summarizes some of the few differences between these three bonds. As you follow the table, you can see that in molecular substances, the particles involved are small covalent molecules. In case of ionic, the particles are positive and negative ions, and in macromolecular substances, it's atoms. Now, when we move on to the part where we have the kind of bonds that arrange, or the kind of bond that hold these particles together, we see that in case of molecular substances, the bonds are very weak forces. In case of ionic substances, the bonds are strong ionic bonds due to the electrostatic force of attraction between the positive and the negative ions. In case of macromolecular substances, these bonds are strong covalent bonds, as we just discussed, like in case of diamonds. Now, when we come to the part of solubility, we find that in case of molecular substances, they are insoluble in water. And ionic solids tend to be soluble in water chiefly because of the fact that water is a polar solvent, as in it is composed of a positive part and a negative part. Hydrogen ion giving the water molecule a positive part, a positive state, and the hydroxide ions giving water a negative part or a negative state. As a result, water is a polar solvent. And when you put in ionic solids in a polar solvent, they dissociate due to their attractions, due to their opposite attractions between the oppositely charged ions. But in case of macromolecular substances, they are insoluble in water because these substances are not charged, made up of charged particles as ionic bonded substances are. And because of the same reason, molecular substances tends not to conduct electricity at all under any state. So does not macromolecular substances. They do not conduct electricity under any circumstance. However, in case of ionic substances, they will not conduct electricity when they are solid, but they will conduct electricity only when they are molten or dissolved in water. So we see the chief differences between these three bonded substances under these parameters. And we have also studied metallic bonding. So if we were to contrast metallic substances with these three, what would we find? In metals, the particles involved would be metal atoms, as in positive ions and negative ions. And they are moving freely about one another. The negative ions are moving freely about the positive ions, giving it positive ions embedded in a sea of electrons. When we come to the bonding part, in metallic bonding, in contrast to them, the bondings tend to be strong metallic bonds. And when we come to the solubility part, as we have discussed before, metals are insoluble in water. And we know, as we have discussed it over and over, metals conduct electricity when they are solid, as well as when they are molten, because the electrons in them are allowed to move freely, and therefore they can conduct electricity freely as well. So guys, this was the final part of this chapter. I hope that in this final part, whatever we have discussed via examples, tables, diagrams, you were able to follow through. I hope you have noted down the key parts of my lecture. I hope you have obviously noted down the tables and the diagrams that I have provided in this lecture and in the previous parts. And I hope by now the concept of chemical structures and the different chemical bonds have been clarified to you. And until the next chapter comes along your way, have a nice day.